Okay. First question. What do you do if momentum is not conserved? If the answer is yes, then you do what we've been doing like in the lab. We have initial momentum of the system is equal to the final momentum of the system. If the answer is no, then momentum changes. You've already dealt with that. That is equal to mass times change in velocity. That's equal to net force times time, which is equal to impulse. We learned how to do that before we learned how to do conservation of momentum. All right. Experiment 5. Okay, experiment 5. We're going to look at explosions today. Okay. Spoiler alert. Explosions in physics don't have to be cool. Like, they don't have to involve fire. Like, it's just when one big object becomes multiple objects, we can say, yeah, that's an explosion. Like, so, I've got this spring-loaded bumper in here stored away. When I hit the trigger, it's going to explosion. So, initially, we're going to keep it at rest. This is cart A. This is cart B. At rest, I hit the trigger. What do you think is going to happen? What's the total momentum of the system? Okay, here we go. 3, 2, 1. 3, 2, 1. Explosion. All right, so run through that, the rest of that. Good.
Is the thingy not like pushes off the bat? Is that a part of the system?
Oh, great question. So we're looking at this before it hits the ends. Okay, so I don't care about when it hits the end post here or here.
What about that thingy that's poking out?
This guy?
Yeah,
That's part of the system. Yep.
Yes, because it's part of the system. But that doesn't make any sense because this is going faster than that. That's really persistent. Oh, but it has more mass. Okay. It has more mass.
I like the darkest
That's never
I was right. Okay, ready, set, I like it better.
Tell your neighbor to answer the last question. Okay. I made these up, so your numbers could be different here. Correct answer is? Correct answer is the same. So the total momentum of the system remains 0. Because the total momentum of the system is 0, so whatever's going one way has to go the other way to cancel it out. Okay? All right. Experiment 6. We're going to do an explosion. However, this time we're going to be rolling to the left. Okay, so we're going to be going this way slowly. I'm going to hit the trigger. Okay, so that's experiment 6. So do the initial momentum of the system for experiment 6. Calculate that.
Wait, what's the last sentence?
0.5.
Oh my gosh, it literally says it. Oh wow. But maybe so let other buttons.
Yep. Okay. You can skip to the next page and enter in the initial momentums that you just calculated. Everybody good with that? Where that came from. Both are going at 0.25 meters a second in the negative direction. Okay. So here we go. Ready? We're slowly rolling to the left. This one goes back slightly. Okay. I'll do it again. Another vantage point in case someone's head was in the way. Here we go. Here we go. It goes backwards. This way it goes that way. I don't care about this hitting that. Pretend like that track kept going. Okay. Go ahead and go back to the side 3, page 3 of that. All right, so here, B changed directions. Is it mathematically possible for something, bless you, that continued in the same direction experience a greater change in velocity than something that changed directions?
Yes.
Is it mathematically possible for something to maintain its direction of motion, but like speed up, have a greater change in velocity than something that changes its direction? If you go from 10 miles an hour to 100 miles an hour versus from 10 miles an hour to turn or stop and go 10 miles an hour in the other direction, you got a change of 90 miles an hour from the 10 to 100 versus from 10 to negative 10, that was a change of 20 miles an hour. Okay, so just because something changes its direction, do not automatically assume, oh, that had a greater change in velocity. Okay. So circle the rest of these, or like do the rest of this. Side 3. All right, here are the answers. Oops. Tell your neighbor why we know definitively that A had a greater change in velocity.
How would you know that
You
without seeing
can't
it
say
visually?
that because math is still a thing.
How do you just know that? That's what I'm saying. If you can't
Right.
see it
So
visually,
think of a different way. There's a definitive way to think about it.
Yes.
Who has a definitive way of why A has a greater change in velocity? There's a way that you can know beyond a shadow of a doubt, like, yes, it does. And it's not just by looking at it going, wow, that's going faster. How do you know? How did I know confidently that A had a greater change in velocity? Andrew.
I should know that.
Sophie. We know that the change in momentum is the same. True? Experience the same force for the same amount of time. Okay? If A has the same change in momentum as B, B is more massive. If it has the same change in momentum as B, then it has to be going fast. Like it has to have a greater change in velocity. Does that make sense? And then you can go, oh yeah, I can see how that works. It's going a lot faster. That's how you read that. You cannot say, wow, it's going a lot faster. That must have a greater change in velocity. That's fuzzy. That is not, you are not rock solid. And it's an educated guess, but it is on a test. You'll be like, I don't know. I feel like I'm guessing here because you are. Okay? Okay, fill in the rest of the make up your own numbers thing and answer the last question. Tell your neighbor the answer to the last question. Tell them why.
Always going to be the same if change in potential is the same, or change in momentum.
What is it when you're
This.
saying
The magnitude.
the change is the same? Yes, but this is asking for the final amount.
Oh.
Do you see the difference there?
Well, will it still be the same?
What is
The same.
same what? Same change, same final.
Same final.
If I give you $20, your change and my change in my bank account and your change in your bank account are the same. Mine's positive and yours is negative. But our final balance is we have no idea.
But
So you can't say.
Unless no, you can, but you can't look at it just with a change. Unless we both started at zero, we'd have the same change. But unless we both started at zero, we won't have the same final amount of momentum.
So then why? Oh, because we did start 0 and lost.
In part 5,
But we started.
correct answer is A, has a greater amount of momentum. Why? The total is going in the negative direction, is going to the left. You got something going to the right, you got something going to the left. The left has to overcompensate for the momentum going to the right. So the total momentum is to the left. Good with that? Okay, experiment 7 is the same thing. We're just going to the right instead of to the left. So this is plus 0.5, and this is plus 0.125, and this is plus 0.0375. Okay, we're just going in the reverse direction as experiment 6. Okay, here we go. Ready? Slowly. Okay. I'll do it again. Okay. So finish the rest of that experiment. Tell your neighbor the answer to the last question. And tell them why.
So it's only going to be the same when we start at 0. What?
I like make sure it doesn't.
Okay, correct answer is B. Why?
Or math, kind of the same.
Nope. You know that the total momentum is to the right. You got something going to the right, something going to the left. The total momentum, sorry, B has to have more momentum than A because the total momentum is to the right. That is the only contributor to the right. It has to overcompensate for the negative momentum.
He said it then last week.
He did.
I wasn't listening.
Okay, good with that?
Now I know.
I want you to go through the rest of the lab, finish those summary questions, and when you're done, you may turn those in either today or tomorrow. Right up here, make sure your name and hour on those. But look through the summary questions. You're welcome to talk amongst yourselves, but don't just be a mooch or a leech and just suck answers off of somebody else.
Wow, that's actually.
Got a review packet due on the day of the final.